All right, welcome to module number 5. Recall that in modules 3 and 4, we had a probability review, and now we're going to talk about some key terminology in machine learning, which we'll often use throughout the course, even before the machine learning module. And after that, upcoming modules, we'll be discussing models. So let's begin with inputs and outputs. We have a machine learning system. There are numbers going in, there are numbers going out, and the features are the explanatory variables. So imagine that you're trying to guess whether a person is going to click on your ad or not, or whatever you're trying to predict. And the explanatory variables could be their zip code, their past browsing history, what they purchased, what car they have, and so on. So features are the variables that can be used to explain the data. The outcomes are what we're actually measuring, meaning did they click, did they not click, how much did they actually spend if they clicked. Now, of course, there could be a lot of explanatory variables. That doesn't mean that all of them are useful. There could be that some of them are very useful and quite a few of them are kind of in the middle, and there could be that some of them are not useful at all. And by the way, recall that usefulness could be counterintuitive. It could be that something is useful, but in a negative way. So you need to add a negative sign, and that's fine. So what we're going to do later on in the course, we're going to discuss feature selection, which is a situation where we have a lot of features, a lot of possible explanatory variables. Maybe intuitively it's convenient to think about 5, but imagine that we have 200, and you want to narrow down the range. So instead of 200, your human user will only need to sift through a few, and feature selection will be helping you decide which features are most useful in predicting the outcomes. The next topic is supervised learning, and we have features and outcomes. And in supervised learning, we want to learn a function that approximates or predicts the outcomes from the features. One style of supervised linear learning is classification. We have binary outcomes, for example, click prediction, and we want to be able to predict the binary outcome from the features. Another type of supervised learning is regression. We have continuous valued outcomes. For example, not whether you clicked or not, but how much did you purchase? And there are various examples, not just the one that I just provided, but also in financial prediction that you're trying to predict whether an asset price will go up or down. And we also discussed regression as part of the polynomial curve fitting. So again, in regression, we have features, we have outcomes. We're going to want to put together a function that explains the outcomes rather well from the features. So that's supervised learning, and unsupervised learning is quite different. There's less emphasis, little emphasis on it in ECE 592, and we don't know the outcomes. So what we're doing instead, we're going to learn the data structure. For example, you can imagine in density estimation that we're going to have point clouds of where the samples are, and we're going to want to perhaps cluster together samples that are nearby. As you can see in this example where we have the 3 green blobs. And unsupervised learning, you can think of it as a clustering approach. Another consideration in machine learning is the types of data that are involved. So in homework 1, for example, one way to approach homework 1 is to separate data into training data and test data. The training data is going to be used to train the model or learn the function. And while using the training data, the rest of the data, which is the test data, you're going to put it aside. And after you train, after you've learned the function, you're going to use the test data to try to verify or validate the model. And this is also sometimes called holdout data, and sometimes this is known as cross-validation. But the idea is you have all the data, you partition it into 2, training and test. Now, this can get more intricate. For example, you can partition into test and training multiple times, and you can check each partition separately. And one of the objectives of having multiple such partitions is to make sure that you're overall result, meaning how well did your learned model work on the test data. You don't want it to be overly sensitive to one specific partition, and you want it to work well on multiple partitions. Finally, there are also computational considerations. An online algorithm is a machine learning algorithm that learns from the input data as it comes along. So you're getting one or perhaps a small number of input data, and you immediately modify the model. And the advantage is that this is responsive. Every time that you got new data, you modified your model. The disadvantage is that oftentimes it doesn't learn so well. And to learn well, we often need a lot of data. And an offline approach, it waits for the entire data, and then you run your algorithm. The advantage is that by processing a lot of data, you have improved learning. The disadvantage is that you need to wait quite a while until we get all the data, and then processing all the data may also be computationally intense. An approach that's in the middle between online and offline is a batch approach. It's hybrid. You learn from chunks of the input data, and after processing a chunk of data, you update your model. So that's it for module number 5.